we discussed about the front end AC to DC converter and how we can control the harmonics or suppress some of the low order harmonics without resorting to high frequency PWM switching. So, the configuration used, I will again draw it for a clarity again. You have the primary transformer, then 2 secondaries, then you have the 2 converters, one is here. We will assume the switches are bidirectional. So, diodes I am not putting now. So, we should assume that diode is there. So, here the transformer, either the transformer leakage inductance or extra inductance, we have to put it to take care of the ripple. Okay, this should be there. Similarly, the second converter, inductance here. Okay. So, these converters, the PWM, this is converter A1 B1, this is A2 B2. For A1 and B1, we will use the same reference wave, that is modulating wave, same sine wave, but the triangle wave for A1 and B1 are 180 degree phase shifted. Okay. For A2 B2, but for the switching sequence for B1 is reversed. So, what is for S1, you will use it for here, the bottom switch of B1. Then here for the second converter, the same modulating signal we use, but the triangular waveforms for A2 B2 are 180 degree phase shifted, but A1 and A2 are 90 degree phase shifted. So, we have the output load is like this. This one will also come here, this one also, this one come here. So, parallel operation. So, by doing this way, what happens? You will have the harmonics like this. You have the Vn here, harmonic order, amplitude, then you have the harmonic order here, number of harmonics. So, you have the fundamental here, then all the harmonics at Fc and its sidebands, that is this one, this is Fc and its sidebands, also at 3Fc and its sidebands, this is 3Fc and its sidebands. All this will get cancelled because of the PWM technique used, sine triangle PWM used for the leg A and leg B. So, last class we told for A, when the sine is greater than the A leg A, sine greater than triangle, top switch is on, then sine less than triangle, the bottom switch is on. Okay. That is for leg A, and for this is true for this converter also, but for leg B, sine greater than the triangle, the bottom switch is on, and sine less than triangle, top on. Okay. This we are using by using this one, and the triangle frequency Fc is equal to 11 times Fm we are using. So, all these harmonics FC, 3FC and odd multiple get cancelled. Now, since these two are parallel, the triangle waveform A1 and A2 are 90-degree phase shifted. So, all the harmonics at the sidebands of F2, that is this one, because of the 90-degree it will get cancelled here in the transformer. Here it may be flowing, but it has opposite effect in the transformer core, and it will not generate any flux, and it will not couple to the transformer primary. So, transformer primary will have the fundamental, then sidebands at 4FC plus or minus 1 and minus 3, that way it goes. Okay. So, this is the thing. Now, let us study how the typical waveforms look like. You have converter 1, converter 2, okay. This is switch. So, let us draw the modulating wave and the sine wave. So, 11 times, approximately 11 times we can draw it like this. Let us draw the this is how to get a feel for it. That is why this is the triangle waveform. We will make 11 times. So, let us draw the modulating wave. We will use the same modulating wave. This is the modulating wave. Now, for the second leg, if this is A, this side is B. So, for B phase, we have the inverted one. Okay, let us draw the inverted one with a different color. This is 180-degree phase shifted. Now, let us draw the switching pattern. Switching pattern, first one, let us take for the leg A. Leg A, which triangle we will be using? The blue triangle we will be using for leg A. So, I will mark it accordingly. A is here. A. So, whenever sine is greater than the triangle, top switch is on. So, here for leg A. And when the sine is less than the triangle, that means we are comparing the modulating wave and the blue triangle waveform. When the sine is less than the triangle, the bottom switch is on. So, if you do, when the top switch is on, this point, the center point with respect to our DC midpoint is equal to plus VDC by 2. So, there it will be minus VDC by 2. So, we can see this comparison, we can take it this way, that is the second one here. during this portion it will be triangle is greater than the sine wave. So, if we use that blue triangle waveform and the so, we are comparing all the time comparing with the blue triangle waveform and the modulating sine wave. So, whenever sine is greater than the triangle, the top switch is on. So, the leg voltage or the pole voltage A with respect to our fictitious center point of the output DC plus VDC by 2, otherwise it is minus VD. When the bottom switch is on, it is minus VDC by 2. Okay. So, the waveform will look like this. This way. All this hatched portion shows that the top switch S1 is on. S1 top switch is on. The bottom one will say 2. Okay. Now, for what is the pattern, the voltage waveform, pole voltage or the leg voltage B0 for the second leg, then you have to use the sine as well as the red triangular waveform. So, we will go to the red marking. So, here red triangle waveform means here. So, the waveform. So, here if you see here, when the triangle is greater than the sine wave, here the switching sequence is inverted, that is top switch is on. So, whenever the triangle is greater than the sine wave, the top switch is on, we will have VDC by 2, the pole voltage waveform. So, this way. So, whenever the here whenever the sine greater than the triangle, what we are doing, the top the bottom switch is on. No, sorry, whenever the sine greater than the triangle, okay, the bottom switch is on, okay, but it is in the reverse of the other phase. So, what we have to remember here, the triangle waveform 11 times the sine wave, and the triangle waveform for the other one, the leg B is inverted, triangle waveform, and the switching sequence for the leg A, when the sine is greater than the triangle, the top switch is on, when the sine is less than the triangle, the bottom switch is on. In the leg B, whenever sine is greater than the triangle, we are turning on the bottom switch. The logic is inverted here. Now, what is the final waveform across the load VAB? That's we are more interested in that one. That is equal to VS0 minus VB0. Let us do the VS0 minus V0. This is the top one is VS0. So, this is VS0 and this one is VB0. Now, VS0 minus VB0, we can do it like that. we can just subtract it. So, these type of pulses we appear across the waveform. That height of this one will be, previously it was VDC by 2, the height of will be VDC. Here it is VDC by 2. This height, if you take it, this height is equal to VDC by 2. That is true here also, but in this case it is VDC. For subtraction, that minus minus get added. So, to make it all the waveform within the page, I have slightly scaled down the height, but the actual height is VDC here. That is VAB waveform. So, if you do the Fourier analysis of this waveform, it will have the fundamental 2 times the individual leg A or individual B. At the same time, it will not contain the harmonics at FC at its sidebands and 3 FC also. The here with one converter, the next higher amplitude harmonics happens at the sidebands of 2 FC. Now, with one more converter, we will try to cancel the 2 FC side also, so that the final high order harmonics happens at the sidebands of 4 FC. So, 4 FC is 11 times, 4 FC means 11 into 44 times. So, 44 times the fundamental. So, we by a very interesting technique, without resorting to high frequency switching, we have shifted the harmonics to very high frequency side. This is VDC. Now, for the next converter, that is a converter, the bottom converter. Again, I will try to draw the figure. It is like this. Here we will say this leg is A2, this leg is B2. Okay. Our AC side is here. So, here with respect to this triangle waveform, for the same A leg and same leg A leg here, it is 90 degree phase shifted. So, let us draw the 90 degree phase shifted waveform. So, this is the one 90 degree phase shifted. This is for leg A2. Sorry, this is according to this one, if it is 90 degree, this is for leg B2, red one. Okay, sine wave is the same. Same modulating wave we are using. So, all the fundamental get added. Now, for the blue triangle of this one 90 degree triangle, we will draw the 90 degree phase shifted. That is this one. This is for leg A2. Okay, leg A2. Now, for the A01, let us draw VA20, let us draw VA20, when the sine is greater than the triangle, top switch is on. That is from here and here, VDC by 2. So, if you repeat for other triangles also, you will get this pattern, but here the height is VDC by 2 and the plus VDC by 2 minus VDC by 2 it will go. So, this is the pole voltage waveform of the second converter with a 90-degree phase shifter triangle with respect to the same leg of the converter 1, that is this converter. So, I will just mark it to get the pulse width, the change of pulse width, that feeling for the change of pulse width. Okay. Then for leg B, we will change to the converter. It will be like this. Sorry, this is the one. So, we are comparing the red triangle with the modulating wave sine wave. Here, whenever the sine is greater than the triangle, the bottom switch is on. When the sine is less than the triangle, top switch is on. The switching logic is interchange, same as before. Only the case is the triangles for the similar legs for the second converter is 90-degree phase shifted with respect to the same the converter, the top converter or the converter 1. So, this is the case. So, again the pole voltage waveform VA2 B2, that is VA2 B2. Sorry, I will the VA2 B2 will be VA2 B2. That means VA2 0 minus VB2 0 will be like this. So, this height will be again VDC, it will go to plus VDC here and here it is minus VDC. So, these are the VA0, VB0 waveform coming across the two converters. Now, if we sum these two voltage, that voltage will have a shape like this, because that the current waveform to get a feeling of the harmonics, instead of summing the current waveform, if these two voltage waveforms you can sum, this may be the replica of the voltage waveform appearing across the transformer, two secondaries and reflected on the primary. But here if you see here, transformer primary we will be giving the sinusoidal voltages, and in this waveform all the harmonics, individual harmonics will be dropped across the leakage inductance only. So, why I am summing, this is not actually happening in the converter, these two waves are never summed, but this waveform when you sum this, the resultant waveform, frequency spectrum of the resultant waveform approximately gives the harmonic spectrum of the suppressed current waveforms. We can get a feel for that one if you do the FFT of this one. So, this is a stepped waveform, PWM with stepped waveform. This waveform will not contain all the FC and its harmonics, FC, 3FC, 5FC and its harmonics will be highly suppressed, and then the sidebands at 2FC. So, this will have only harmonics, the 0 line is here. This will have the harmonics only at the sidebands of 4FC. So, you will get a stepped wave yearly. Okay. And the primary current will be more sinusoidal here. So, we will have a simulation study of this one later. But now the PWM technique we know it. Now, how to generate the required VM? So that the required VAB is generated such that the transformer primary always you to draw unity current with unity power factor, or the current drawn from the transformer's primary side will be nearly sinusoidal and in phase with the mains. So, we will study that part now. Before going to the study controller part, see one more thing we have to learn here. How to design this L and C. Let us study the how to design the inductor for one converter. Let us draw the converter once again. This is the mains, this is the inductance, this is the switch. Okay. Here. So, this is our A and this is B. Okay. Now, according to the phasor diagram, with unity power factor, this is Vs and this is Is in phase with, that is this current Is in phase with Vs, and the drop across inductance L will be for power flow from source to the load, it will be like this, otherwise it will be like this. So, VAB will be like this. This is the VAB. Okay. Now, so Vs plus Is. If you take the fundamental component of this AB, okay, AB fundamental component, that we will represent as VR. VR. The VR is the fundamental component of the VAB, PWM signal, PWM waveform. Okay. That is VR, fundamental component of the VAB PWM waveform. Now, if you do assuming the harmonics are highly suppressed, due to fundamental there is a drop across this inductance. So, from this diagram, what is the relation between the fundamental voltage and the inductive drop, that is this one, and the VAB waveform here, it will be equal to VR is equal to root of Vs square plus L omega, omega is the mains frequency, this is the L, into Is square. This L omega Is is the peak value of the sinusoidal current here, L omega is the drop. Now, this VR is generated by modulating the sine triangle PW. Okay. and from the previous sine triangle PWM, and our V0 is here. This is our E0, sorry, E0. So, VAB will be the from the previous sine triangle analysis what we have done 2 days before, the VAB for one leg, the maximum amplitude of VA will be proportional to the maximum will be equal to VDC by 2 that or E0 by 2. So, when subtract A and B, the maximum value, the fundamental maximum value of VAB will be equal to E0, that is the maximum voltage VR we can get. But in all practical applications, we will not go to the extreme modulation. If you take a sine triangle like this, we will not go to this range. See, if you go there, the pulse would become very narrow, the system may not respond here. So, we will always restrict the modulation index, that is the height of the sine wave, modulation index M I will say is equal to our VC value by VM maximum value. Will be always theoretically this will be equal to 1, but we will restrict to maximum, it will be equal to 0.8 for practical limitation. So, from here VR will be 0.8 of the maximum E0, the output E0. This will be equal to root of Vs square plus L. For a 50 hertz operation, omega is equal to 2 pi into F, F is equal to 50 into IS maximum. How do you find out this IS maximum here? How do you find out what is the maximum IS? So that from these two equations, from this equation, let us find out what is L. We will square this one such that VR is equal to, as I told, will modulation index will go up to not to 1, it is only 0.8. So, 0.8 E0 square minus Vs square, okay, divided by omega square Is square is equal to, or square root of this one will be equal to our L value. Now, if you see here, this L value depends on Vs we know, E know. How to find out this Is? Omega we know, omega is equal to 2 pi into F, our mains frequency. So, how to find out this Is? Is varies with our load, that means load which is connected to here, the what load it is coming here. This is DC voltage, so load. So, maybe Is we can find out from the power balance. See, output power is equal to A0 into I0, output power, okay. And for with the unity power factor, we will assume the efficiency of the system is, it is lossless system 100%. So, input power should be equal to output power. This is the output power. Output power. This will be equal to input power is how much? That is Vs RMS into Is RMS. Okay. So, E0 we know, I0 maximum load current we can find out, Vs RMS is known. From this one we can find out what is the, for a maximum load, what is the Is RMS. From the Is RMS we can find out Is peak and square it, you will get it. So, L this way we can find out. Now, how to find out the value of this capacitor? That is very important. So, let us find out the next one, how to find out the value of the capacitor. Okay, let us draw the converter once again. That is only one side converter only we will draw it. This is our input source here. Then you have this is the A point, A leg. Here is our B leg and your capacitor. Capacitor has to take care of the ripple current coming from here. If this is the I0, okay, the current, ripple current coming through this current, the current which is coming from here, let us say this is IL. IL contains, this IL contains DC current plus the ripple part. The ripple will pass through the inductance. That is the oscillating part, not the DC part. The fluctuating part, it will go through the capacitor, and capacitor we should choose it such a way it should give a stiff DC link. That means due to the ripple current, fluctuating current, the voltage ripple across this one should be as small as possible. Small means how much? Okay, 5% of the DC. We can have only that much ripple. So, let us find out what is the ripple current coming here. Here again, if you see here, this is VAB, fundamental component of input power of this converter should be also be equal to output power of this one. So, the input power to the converter is equal to VRT into our IST, that is coming from here. This is the IST. Okay. This current input, assuming 100% efficiency, VST and IST should be also be equal to, this is we can assuming this is equal to E0 into I0. Now, sorry, V0, that is sorry, not I0, that current, E0 into the output power, input power should be equal to the output power. So, output power is equal to E0 plus IL into I0. So, I will take IL here. So, what is VRT into IST? VRT is equal to, if you take, this is Vs, this is Is, this is our fundamental VRT, and this has a delta here. Okay. So, VRT will be VR sin omega t minus delta into Is sin omega t. Okay. So, net current IL is equal to VR Is into sin omega t minus delta into sin omega t divided by E0. This is the current IL coming out of this one. Okay. Input power is equal to output power. Okay. Now, if you see here, this can be extended like VR Is divided by E0 into cos delta minus cos 2 omega t minus delta. So, IL contains a DC part, that is DC. This is the DC part, that is equal to the I0, and there is a fluctuating part, that is 2 times the input frequency. This will go through this capacitor, that is this will go through this one, this part, this one, the one which is this one. Okay. So, we have to design the capacitor for this 2 times the frequency. There is a second harmonics current flowing through this one. So, again once again this is the input power, sinusoidal fundamental, sinusoidal current, input power, voltage into current. This is the output power from the converter. Now, VRT from this definition, it is VR into sin omega t minus del into IS sin omega t. So, the IL which is coming from here, if you see here, you will get this equation, but when you convert to this one, there is a 2 has to be there, okay, because sin A, sin B we are converting to cos. So, this 2 has to be there, sorry, there is a mistake here. So, I will correct that one now. So, this there has to be a 2 here, okay, 2 is 0. So, this current, this into cos 2 omega t, this value into cos omega t will, cos 2 omega t will flow through this one. That will generate a ripple current across this one, and let us see what is that current. If this is cos 2 omega t, we will integrate approximately, this is the ripple peak, let us take the ripple peak, let us take as IL hat, ripple peak, if you integrate, divided by 2 omega c. If you do the capacitor, capacitor is equal to integral, the voltage delta V is equal to integral 1 by c I dt. So, that cos this function, if you integrate, you will get this one. So, this will be, you want, is equal to 5% of the delta V, 5% of our less than or equal to 5% of 0.5%, 0.05 of E0. This has to be there. So, E0 no, IL peak V no, we can find out C. So, if you see this equation, I will write it here. The C will be from this inequality here, C should be greater than or equal to IL hat, that is a ripple peak, that is from here, IL hat divided by 2 into 0.05 E0, okay, divided into omega. So, from this equation we can find out the value of C approximately. So, C should be greater than this value. Now, L and C we have found out. Now, what we want? We want to control the output voltage. So, what is the control block we require? What is the VR we have to generate? That is fundamental of VAB we have to generate for all load conditions such that the input current is in phase with our mains voltage. How we will do it? Control block of the front end converter. What we want here? We want a output V0, output E0. So, this is our reference. So, reference I will mark it as E0 star. Okay. So, this is the reference. Whatever we want, we can fix it reference. So, it will be compared. That means our output voltage we have sends and feedback to this one. Okay. So, the moment we are comparing the reference plus the feedback, this is the feedback. There should be a controller. So, what type of controller we will decide later. We will put just controller. Okay. So, controller what it should give? It should give the IS. Why? Because anytime the E varies, changes with respect to reference value, that means there is a change in the capacitor voltage. That shows there is a change in the output load current. So, any change in the load current assuming 100% efficiency and the input power should be equal to the output power. So, for the required current there should be a input current required. So, this indicates any change in E0 with respect to E0 indicates that there is a current demand, change in current demand from the main side. So, this will indicate to the IS, load current IS, which is flowing through the inductance or which is taken from the mains, this IS. This IS again we have to sense it from our mains, we have to sense it from here. I will just draw it here, this is our input, that is this is the current IS, this we have to sense it using a Hall effect sensor, LEM current, a current sensor we have to use it and we have to properly scale and give it here. So, here also we need a current controller to control. What type of controller we are not, we do not know. So, this controller what it should give to get the correct IS and IS star and IS to match, what is required is the fundamental component of the AB with the PWM. It should be the required VAB or reference value, you should get it. So, the VAB, the reference value for VAB is the output from here. So, this will go to the VR reference. So, controller we take it with for only a one converter, for the two converter appropriate gain of 2 we have to give at the various places, but the same controller is used, we can use it for the both converter. So, this is for VR star. So, this VR star it will go to the PWM converter, PWM, pulse width modulation of the converter. So, converter will give what? Give the correct VR. This is the reference value and the converter will, PWM will give the correct reference value. Now, this VR so, if you see here this is Vs. So, Vs plus L into dis by dt is equal to Vr here. So, Vr already we got here, we know the Vs value. So, if you want to this Vs, so Vs this is plus Vs minus Vr, okay, Vs plus L into di by dt is equal to Vr. So, Vs minus Vr is equal to L into di by dt. Okay. So, this you integrate with the gain of 1 by L. Here you will get the IS. This IS, these are actual currents, we have to bring it to the controller side. So, we may require a gain function to reduce it, or if you want to filter it, you may have filter also will be there. We will put simple gain function Ki, current gain. So, that IS reference and IS, okay, if it is for used, if the controller is built using analog controllers, maybe IS can vary from plus minus to plus 10 only. So, actual current when we sense it and bring it back to this one, there is a gain function is required. Okay. This is how you do it. Now, this is a inner current loop is there. So, here if you see here again I will explain, you have the E0 reference and feedback we are taking from the converter. If there is any mismatch in E0 and E0, it reflect on the type of load current required. Load current, there is a variation in the load current. So, if there is a variation in the load current, that should reflect on the input current drawn IS. So, this controller output should point to the IS. This IS and actual current IS we will compare, and this compare out will give you a controller. So, this controller should, this IS star and IS should match, controller should give the correct VR reference, that is the reference for that or the modulating wave for sine triangle PWM. So, if the correct waveform is given, the PWM, the converter, PWM converter will give the correct VR here. Now, this is the converter output. This VR or Vs minus VR, integrator 1 by L integrator will give the IS value. This IS you step down, you can feedback it here. Now, IL we got. How to find out the, now how do you get the E0 value? How do you make the block diagram for the E0? So, if you see the from the power balance, okay, with the unity power factor, VSIS, RMS VS, IS, these are the RMS values, is equal to E0 into I0. Okay, E0 into I0. Vs, Is are in RMS value. So, if you take the peak value, if Vs and Is are peak value, that Vs peak, Is peak divide by root 2, divide by root 2 is equal to A0 I0. Okay. Is we already know it. So, Vs Is divided by 2 E0 is equal to our I0. Okay. This is the DC value current. So, if there is no disturbance and the load is pakka matching, this I0 will I0 coming from here. So, we have designed the, we are worried about all the DC value. We have chosen the capacitor such that the fluctuating part will go through this one, and capacitor value we have chosen such that the voltage ripple is very minimal. So, the DC value it will go here, this I0. So, this block already we have to use it this way. You already know Is. So, from the Is there is a gain block. This gain block is equal to, this is the Vs, not I, this is Es into Vs peak, Is peak, Vs peak. Okay. So, Is is coming here, Is we know it, we can generate the Is value here, get the Is peak value. Is into Vs divided by 2 E0 is our I0. I0 at any instant any load change happens. If I0 and the I load are same, then the difference is 0. So, there is no disturbance in the capacitor voltage waveform. But suddenly load changes, increase or decrease, I load will change immediately. So, unless that is indicated to the converter I0, the immediately there is a fluctuation can happen in the capacitor voltage. So, this difference immediately go to the capacitor. That will generate a ripple 1 by C, this is the integral. That will give the V0 side. This V0 will feed back to this one. This is the complete block diagram for controlling the converter. So, again I will say how this one, you have the E0 reference and E0 feedback, that we are taking tapping from here with the proper sensors and we are giving it there. With the proper sensors we are taken from here and we are giving it here. Okay. Now, when the load current and the DC value of the current coming from here, this converter, when they are equal, the capacitor voltage will not fluctuate, capacitor voltage will be steady and the controller will be in the steady state. But due to sudden change in load, that is not in our control, this I0 can change, but our controller is giving us some steady ID. Unless this is modified, VR is modified, this will not change. So, sudden change in load, the difference will immediately go through this one and there will be a change in the capacitor voltage V0. That change in current, difference in moment sudden change in load I0 minus IL load integral 1 by C integral this difference, that we will feed back to this one here. Okay. Now, the moment change happens, immediately IS has to change. So, IS we are sensing from here, IS is given. Any change in the IS through a controller, we will generate the correct VR. We will give the power converter, so that the power converter reference waveform, that is the modulating wave, we will give to the converter such that this converter will give the correct VR. So, from this equation, VR, Vs minus VR, integral 1 by L gives the current IS here. That IS, instantaneous value is IS divided by K, we will feed it here. So, here if you see, this current is a sinusoidal current and this current we are controlling with this one. Okay. And all our controller here is due to through PWM. So, we will assume the PWM frequency is so high. So, during the control action we can assume this IC, the sinusoidal part of this current IC with a small ripple is not changing much. So, we are using a sinusoidal current reference and sinusoidal current feedback here. Then that is one of the simplest way of doing the thing. Otherwise, there are other way to convert this converter alternating current to the DC equivalent and then do the controller. Then you require other signaling processing. So, here what we assume, the PWM action is so fast during that small moment, IS reference and IS feedback are not, sinusoidal feedback are not changing. There is not much variation in the IS. So, what we have to give this IS value, peak value of the IS reference comes. So, we have to give a sinusoidal reference here. So, with that sinusoidal reference IS should be in phase with our mains voltage Vs. So, that will take care of the unity power factor. So, this IS will break here and this controller because we know this IS is a sinusoidal current. So, this current also has to be sinusoidal. So, this sinusoidal current we are assuming that control is through PWM with high frequency. During that PWM operation, this IS and ISR, there is not much change in the IS and ISR. So, but we want unity power factor. So, this IS what is done should be in phase with Vs. So, we should generate a sinusoidal reference waveform in phase with this one with the unit amplitude, and we should multiply with this IS and give it here. So, we have to modify this part. Let us see how we can do that one. So, the controller has to be accordingly modified. So, controller output is here. Okay. Then we will generate a sinusoidal signal, okay, which is in phase with our VST, that is sin omega t time. We have to generate a sin omega t time with the unit amplitude. This we should multiply these two. We have to multiplication block. I will make it like this. It's a multiplication block. You give it here, and this one you should give it here. Output should be given here. So, this sin omega t, which is in phase with this one, that will ensure that this current drawn IS will be in phase with Vs all the time, and you have to generate VR. So, here what is more important is how to find out this controller and this controller. What is the function of this controller? Such that input should track the output, or the output should track the input as close as possible. So that any change in IS, with IS immediately we have to generate the VR. So that controller has to take care of that one. So let us study out some of the standard controller, like P controller is there, PI controller, PID controller. So if we use this controller with how the whole system, the current block, first we will start with inner current block, how inner current block will work, that we will study in the next class. So we will go to the controller, and what are the controller, standard control, what are its problem, then we will try to fit in one of the standard control blocks and we will choose the correct one.